Good afternoon. I'd like to welcome you to this afternoon's Bullard Lecture. My name is Kathy Constable. I'm the president of the Geomagnetism and Paleomagnetism section. And this is our signature buoy lecture for the AGU meeting. It's named after Teddy Bullard, who was a distinguished geophysicist who spent his career at Cambridge University, his summers in California, and then moved to California after he retired. He was a geomagnetist and marine geophysicist throughout his career, so it's appropriate that we name our section lecture after him. He was doing geomagnetism right up to the day that he passed away. The purpose of our Bullard lecture is to communicate important and exciting science to the geomagnetism and paleomagnetism section and to other people across the Union. And today's talk is going to be presented by Jim Channell. I should just say a few words about Jim Channell. I wanted to say something outrageous about him, but all I could discover is that people think he works extremely hard. So he must have a very boring life, I suspect. Anyway, he began his career in Newcastle in the United Kingdom, working on the paleomagnetism of the Mediterranean. After his PhD, he had a spell in ETH in Zurich for a few years, then moved to Lamont and eventually settled in Florida, where he seems to find the climate to his liking. Jim is an expert on the marine sediment record of the geomagnetic field. That's what he spends a huge amount of his time working on. He's a fellow of the AGU. He's been a Joides Distinguished Lecturer and an awardee from the GP section already with the Gilbert Award. And it's our pleasure today to listen to him. I have a certificate here with which we're presenting to him, which has the title of his talk on it, because I couldn't find it on the program. And it's Excursions and Paleointensity, Integration of Magnetic and Oxygen Isotope Stratigraphy. Thanks, Jim.
Thanks. Thank you very much, Kathy, for the introduction. And I wanted to mention that before I get going on this, I wanted to acknowledge my collaborators in this talk. Specifically, my student Shuang Xuan, who's been instrumental in our work over the last couple of years at the University of Florida, and also Dave Hodel, formerly of the University of Florida, now at the University of Cambridge. I never met Teddy Bullard, although when I started working in geophysics, I soon became aware of his influence on our discipline. And he presided over a sort of golden era of geophysics at Cambridge, particularly in the 1960s and 70s. Before I got into geophysics and my life was more exciting, I was influenced by the Bullard family in other ways. I grew up in the east of England, and these sorts of establishments were scattered throughout that part of the country. And the Bullard brand was very popular at that time. Unfortunately, it was bought out by a mega brewery sometime later and almost disappeared from view now. But getting back to the geophysics, the polarity timescale that we're all familiar with, the template for that record comes from the marine magnetic anomaly record. And as you know, the stage boundaries are correlated to that record through biozonations. And we have a sort of informal correlation of these stage boundaries to the polarity record that's never been really formalized by the stratigraphic commissions. But nonetheless, it's widely appreciated that in order to generate geologic timescales today, the polarity record really provides us with the thread to which we correlate other facets of geologic time, whether they be biostratigraphic, chemostratigraphic, or radiometric. And so it really has become central to our construction of geologic timescales over the last 160 million years. The efforts to calibrate that polarity record are therefore really vitally important. And in the timescales published by Candy and Kent, as you know, they took mainly radiometrically calibrated points on the polarity record and then interpolated between those age points using assumptions related to spreading rate. In the last 15 years or so, the astrochronologists have provided us with enhanced calibration of that polarity record, beginning with the Pliocene and now have extended through the Miocene and into the Oligocene. And if we look at a plot here of just reversal sequence in one of the astronomical timescales, the one published a few years ago by Lorenz et al., and just compare the ages of the Candy-Kent timescale shown in this green one here, and astrochronologies that have post-dated the Lorenz timescale, in other words, post-dated 2004. And we see that the story is not yet over. I mean, the Lorenz et al. Timescale is going to be refined in years to come. And clearly, however, there is a convergence in these astrochronologies that's beginning to generate a more robust age model for the polarity record. And we can expect in the next decade or so that these astrochronologies will continue through the Cenozoic. What I want to talk to you today about, though, is more magnetic stratigraphy within polarity crons. And this sort of work has been made possible by the ocean drilling program through the JOIDES resolution and the piston coring technology that is part of the drilling ship. And not only the drilling technology, but also the ability to correlate holes from a site in real time and direct the drilling operation as it's going on in order to ensure complete and pristine recovery of the sediment record at any site. Most of the sites that I'll discuss here were sampled during one ODP leg in 1995 and an IODP leg in 2004. And some of the sites I discussed, the locations are shown here, mainly in the North Atlantic. This is one such record. This is declination, inclination, this MAD value here, which is the statistic we use to tell us how well we're defining the magnetization component. This is a record just showing you part of it from 700,000 to about 1.9 million. And this is the Bruns Cron. This is the Matuyama Cron. This is the Jaramillo and the Olduvai. And these are the excursions that are observed in this record from the North Atlantic. And these excursions have become an interesting and intriguing feature of the magnetic record within polarity crons in the last few years. If we compare that record with another record from Site 984, we see that the same excursions are recognized when those two records are placed on their isotopic age models. And the two sites have rather different accumulation rates and different thicknesses. Traditionally, we measure this type of data using U-channel samples, each about 1 centimeter, so at 1 centimeter intervals. So a record like this for, say, 984 would represent some almost 17,000 stepwise demagnetizations. And then the MAD value here is calculated on the basis of a particular demagnetization interval. So you can see low values of this quantity represent better defined magnetization components. And clearly in places where the MAD values go to higher values, you could reduce those by going in and actually looking at the individual Zijderveld plots. But this is calculated in this diagram on a particular demagnetization interval, 20 to 80 millitesla. So this sort of excursion record, then, if we look at individual excursions, and this just happens to be one called the Bjorn excursion at 1.25 million years, it illustrates this excursional record is observed over about 80 centimeters of sediment core. And we can plot these directions. This is declination, inclination, and the MAD value again. We can plot these directions in terms of VGPs, or pole positions, virtual geomagnetic poles. And I'm not implying here that the directions need to be associated with dipole fields, but I'm just using the plot of VGPs to depict the directional change during the excursion. But this is one that occurs in the Matuyama Chron, and during the excursion, the VGP goes to high northerly latitudes and back, and these are three holes from the same site. They don't follow exactly the same path, but they're in fairly good agreement, indicating a full polarity reversal. Similarly, we could look at another excursion. This is one from the Bruns Chron, 188,000 years, and this is from the two North Atlantic sites, 983 and 984. These are different holes at these two sites, and we see that the pole goes through Africa to high southerly latitudes and back. This is a break here, but generally the path of the VGP is through Africa and back through the Western Pacific. And it's reasonably consistent for the two sites and from holes from those two sites. Again, this is the same excursion at two other sites here where the VGP goes to high southerly latitudes and then back again. And essentially it's again through Africa and back through the Western Pacific. And I would contend that excursions represent full polarity reversals. The better records of excursions tend to show full polarity reversal. In other words, directions that go through approximately 180 degrees. Where we don't see that happening, I would contend that it means we're not adequately recording the excursion. What about the duration of excursions? Well, this is one example. I plotted on a depth scale here, but it's based on the oxygen isotope age model, and it shows this is declination, inclination, and the paleointensity proxy, that the directional change associated with this excursion, which is the Iceland Basin excursion at about 180,000 years, represents about 3,000 years for the directional change, according to the oxygen isotope age model. And these different records here are from different holes at the same site. So about 3,000 years would be the estimate of the directional change for that particular record. This is a record that Joe Stoner showed us on Monday, and it's a Lechamp record from the Southern Oceans. And here we see that this is a paleolatitude of the directional record, paleolatitude, and clearly the paleolatitude goes to high southern hemisphere latitudes during the Lechamp excursion at about 41,000 years. This is the paleolatitude, this is declination, inclination, and the black curve here is the paleointensity. Here then the duration estimate would be closer to 1,000 years for this particular record. So the conclusion would be then that excursions are extremely brief phenomena and that they represent full polarity reversals. And that's not just based on the observations I've shown you, but on other records of excursions. The better records represent full polarity reversals. Now, one of the things we can't really avoid talking about when we're talking about excursions is the Arctic, because the Arctic has been particularly fertile ground for the recording of magnetic excursions. There have been numerous excursions in sediments from the Arctic where mean sedimentation rates are just a few centimeters per kiloyear. Now, in the North Atlantic, we would never expect to see excursions recorded in sediments with accumulation rates less than about 8 to 10 centimeters per 1,000 years. And yet, in the Arctic, where sedimentation rates in much of the Arctic, depending on where you are very often less than 2 centimeters per 1,000 years, we see a lot of apparent excursions. Now, because the age control of sediments in the Arctic is poor, because we generally don't have oxygen isotope data, and there's very little we can use to generate chronologies, there's a lot of flexibility in how excursions are correlated and labeled. And some excursions that have been found in the Arctic are apparently unique to the Arctic and have not been observed elsewhere. Now, if we discount that the field manifestation is somehow different in the Arctic than elsewhere, this phenomenon needs further investigation. And the way I want to start this is just by showing you some of the recent age data that has come from some cores collected from the Mendeleev Ridge, which is, that's this region right here, okay, where you can see the dots in red represent the cores that we've studied from the Mendeleev Ridge. We've also been looking at a core from the Lomonosov Ridge and one from Fram Strait. These red dots here represent the amino acid racemization ages from this particular core, and these are consistent with limited radiocarbon ages represented by open triangles here, representing that at about 5 meters depth in this core we're somewhere in isotopic stage 7. There's a limited amount of this type of data from a core collected on the Lomonosov Ridge, and that indicates somewhat lower sedimentation rates. Now, this is an inclination record for this core published some years ago in 2000, and an interpretation of this inclination record in this core by a recent interpretation by O'Regan et al. Gave this apparent change in inclination here from positive steep values to negative values associated with an excursion which is called Biwa 2. Now, Biwa 2 has its origin in a Japanese lake called Lake Biwa. It's really not had very clear recording or recognition anywhere else. And so we have to throw some skepticism on the fact that this can be recorded in the Arctic. So let's look at this core. This is one of the ones that we've studied here. This is from the Mendeleev Ridge, and here's the change in inclination that we see somewhere in stage 7, which some people would like to correlate in with this inclination change on the Lomonosov Ridge. So let's look a bit more detail at the magnetic properties of these Mendeleev Ridge cores. This is just showing the top 5 meters of a core collected very close to the core shown in the last image. And this is the MAD value, declination, inclination, and the NRM intensity. And you can see both blue and red dots here, which are representative of the component directions determined using 2 demagnetization sequences. The reason why we did this was we wanted to make sure that these directions were not some sort of artifact of ARM acquired during AF demagnetization. So this was why we went through this process of demagnetizing at each level in 2 demagnetization sequences. In this case, XYZ and then ZYX, and then measuring after each demagnetization sequence. You see the directions don't really change with demagnetization sequence. So we can explain these intervals of negative inclination in terms of some artifact associated with our demagnetization process. And clearly, from our age determinations for this core, as limited as they are, we're clearly in the late Bruns here. So the question is then, what is the origin of these negative inclination component directions which we see in late Bronze Age core from the Mendeleev Ridge? And the Zijderveld plots for this demagnetization, just some selected Zijderveld plots from this core. These are AF demagnetization, these are thermal demagnetization, and they're taken at the same level in the core. So this sample is taken from the same level as this sample, this one from the same level as this one. And what we see is that this is incidentally U-channel data, and this is discrete sample data. This would be an interval where you're defining a magnetization component which has positive inclination, and the red represents the projection on the vertical plane. So this would be a positive inclination component direction resolved during AF demagnetization. This would be an example of a sample where you see a negative inclination component resolved by alternating field demagnetization. This is another example of a negative inclination component resolved by AF demagnetization. As you increase the peak field, the points go towards the origin of the plot. Similarly, this one, this is a negative inclination component. These negative inclination components are fairly well defined by the AF demagnetization process. And those are the negative inclination component directions I showed you in the last image. Now, when you look at the thermal demagnetization data, you see for this sample, the thermal demagnetization data indicates that that component is also quite well defined by the thermal demagnetization process, and it looks like a fairly regular decay of the magnetization vector towards the origin of the plot. But when we look at these diagrams, we start to see something very interesting. We start to see that the negative inclination component, which is this one, in the thermal demagnetization, is captured by demagnetization in a very discrete interval between about 175 degrees Celsius and about 300 degrees Celsius. And that's true of a whole bunch of samples, that it's between about 125 and 300 degrees Celsius that this negative inclination component, which is the same component we believe we're seeing with AF, is unblocked in this rather discrete temperature range. Now that immediately to a paleomagnetist would lead us to think that perhaps that component is carried by an iron sulfide. And in fact, by looking at the thermal demagnetization of three-axis IRM, you could make the case that the soft component, which is the way this works is you magnetize the sample in three orthogonal directions with different DC fields, and then thermally demagnetize the sample and look at how the soft component, the medium component, and the hard component respond to increasing temperatures. The interpretation of this type of plot would be the soft component is carried by magnetite with a maximum blocking temperature of about 580, and the medium coercivity component is largely carried by an iron sulfide with maximum blocking temperature somewhere around 300. And then the hard component is very weak, and that's why you get all the scatter. Just looking at another set of thermomagnetic data, you can see that the magnetic moment as a function of temperature shows this two-stage decay with temperature. This would be then the iron sulfide. This would be the magnetite in the sample. And this is just a cycling experiment where you heat the sample up, let it cool, heat the sample up, let it cool, heat the sample up, let it cool, where the cooling curve is in blue and the heating curve is in red. And this would indicate that as you heat, you start to change the iron sulfide into a more magnetic phase, which is probably magnetite. Now, the iron sulfide we believe is greigite, and this is based partly on low temperature data, but I don't want to go into that. We can use the IRM acquisition curve plotted on a log scale of applied field to try to look at these families of coercivities that may be represented by the magnetite and the greigite. And the way this works is you determine the derivative of these IRM acquisition curves, which is shown here by the green dots, rather scattered, but you can put a smooth line through those points, and then using a method that's been advocated by these authors listed here, you can determine the log normal distributions of coercivities. You can model that curve using these log normal families of coercivities. And although the individual data is highly scattered, if you do it enough times, you can convince yourself that you do actually see these two coercivity families, one shown in red here and one shown in blue. And these are the ones that, for different cores here, we would associate perhaps with the magnetite and the gregite. These have rather similar coercivities, but you can split them using these, this analysis of IRM acquisition curves. So in conclusion then, we have this very peculiar situation that we have these negative inclination intervals in late Bronze Age cores where the negative magnetization, or the component with negative inclination, is apparently carried by the iron sulfide gregite. Now, how this can occur is a puzzle. You're left with very few options. Gregite is almost certainly an orthogenic mineral in these sediments, and you're left with the option that the gregite must somehow acquire a negative inclination magnetization through some partial self-reversal process in CRM. This is something that is still unclear to us, but it's something that we're pursuing. So in the light of what we know then about excursions within the Arctic, let's summarize the situation for excursions in the Bruns Kron. There's a number of summaries of excursions that have been published in the last 10 years, and you can see that there's been little agreement on the age or the labeling of excursions within the Bruns. Many of the names associated with excursions have actually come from, for instance, the Norwegian Greenland Sea, Fram Strait. All these names, some of them are unique to the Arctic. I'm going to summarize what I think here are the best defined excursions within the Bruns Kron, and I've chosen to label them, some with traditional names, some with less traditional names. But these are the excursions that I think are well established for the Bruns Kron, and I would say that there are about 8 of them. For the Matuyama Kron, the excursions have been detected not only in sediments, which is summarized by this column, and there are about 9 to 11 excursions that have been found in the sedimentary records, mainly from the North Atlantic sites. Some of these have also been found in volcanic sites where the ages of the excursions have been established by argon-argon dating. So our conclusion would be that there are perhaps 9 or 11 excursions in the Matuyama Kron. Now the question is, are these excursions part of the same family as regular reversals? And many people have chosen to think of the reversal process as or the distribution of reversals as a Poisson process. And you can demonstrate this by separating polarity Kron durations into 30 kiloyear bins, and whatever time scale you use, you see a sort of deficit of polarity Krons in the youngest bin. And this would normally be interpreted as the fact that we haven't recorded the very brief excursions that are part of this family of polarity Krons. One way in which you can seek to understand this better is to use a simulation of the Poisson process by increasing the number of reversals within the Cenozoic. So let's say we start at 50 and we increment the number of reversals in the Cenozoic by 10. We simulate the Poisson process for that number of reversals. We then plot the number of observed reversals, but we exclude all the reversals associated with short crons, in other words, crons with duration less than 30,000 years. We plot that against the number of short crons. Now what happens is you increase, in these Poisson simulations, you increase the number of reversals, you slowly increase the number of observed reversals, but then what happens is as the number of observed reversals increases, you're of course subtracting the short crons, so the number of reversals minus the short crons then starts to decrease as you increase the number of reversals in your simulation. Now let's suppose that crons with duration greater than 30,000 years have already been observed. So all the crons with duration greater than 30,000 years have already been observed. And if we take the two timescales, CK95 and the astronomic timescale, Lorenz et al. Timescale, the number of reversals is about the same. And so we would expect the solution for a Poisson process to lie somewhere on this line. Okay? Now, it's unlikely that it's going to lie here simply because for the Cenozoic, this would generate about a few tens of short events during the entire Cenozoic for this solution. We already know from the last 2 million years that we have a minimum of about 14 or 15 events. So the solution should lie somewhere here or above along this line. However, if the excursions were to be part of a Poisson process, it would require that we would have to have about 35 excursions per million years in order to satisfy that condition. That's probably unlikely. So what that means is that the excursion process is distinct then from the normal reversal process. Now I want to go on and talk a little bit about what I call the correlation conundrum. And this involves the use of not excursions now, but paleointensity records in stratigraphy. This is just a diagram of the famous Deloitte record from the Greenland ice core, and this is the Deloitte record from the Santa Barbara Basin. And in this diagram, you can see that these features in the Deloitte record from the Santa Barbara Basin have been correlated to the Greenland ice core record. This correlation supposes a synchroneity for which there may not be any other evidence. And so clearly, in order to understand features in the climate record that may involve leads and lags and relationships in timing, we need to improve our stratigraphic control on these sorts of marine sediment sections as represented by this Deloitte record from the Santa Barbara Basin. How can we do that? How can we generate the improved stratigraphies? Well, if you look at a Deloitte record, say from the last 80,000 years, apart from the last termination, there may not be much in the way of features within the Deloitte record that you can use for correlation in the last 80,000 years. Compare that with paleointensity records. This is a paleointensity stack from the South Atlantic. This is a paleointensity stack from the North Atlantic, published some years ago now. And you can see that the variability of geomagnetic field intensity gives you the potential of being able to vastly improve your means of correlation if you can combine the paleointensity record with the isotope record. Now, the way we generate paleointensity records is by use of the NRM magnetization intensity and a lab magnetization, and we can relate these to the ancient field and the lab field by something we call the magnetizability. And we can rewrite these equations like this, such that if we assume these are constants, then we get the ancient field from the ratio of the NRM intensity and the lab magnetization. The lab magnetization is usually an ARM over IRM or IRM. These are lab-induced magnetizations. And the way we like to do that is if we look at NRM demagnetization and ARM or IRM demagnetization, we look at linear segments of these plots where these are the peak demagnetization fields, and we calculate the slopes associated with these linear segments. Say you might choose 45 to 80 millitesla in this case as a linear segment, calculate the slope, and then use the correlation coefficient, or the R value, to allow you to understand how well that slope is defined. Similarly, with ARM acquisition, you can do the same thing. NRM demagnetization against ARM acquisition, and determine the slope through a range of acquisition and demagnetization fields. This is a record from the North Atlantic site 1308, and I want to use this record as the sort of reference record for generating a paleointensity stack. This is 110 meters of record here, placed on an age model from the oxygen isotope record, and it goes back, as I say, 1.5 million years. This is the paleointensity record from that core, and these are the two paleointensity proxies we use. They're ARM over NRM over ARM slope and NRM over ARM acquisition slope. These are the two paleointensity proxies. These are the linear correlation coefficients that we can use to gauge how well those slopes are defined. This is the oxygen isotope data for that core that goes back to stage 50. And this is the inclination record that I showed in the last image. Let's now use that as the reference record and derive a stack by correlating other records that have coupled paleointensity and isotope data. Now that is a rather limited number of paleointensity data, actually, that have both paleointensity and isotope data, because we want to do a coupled correlation. And these are the cores that we selected, and their references for these data is given down here. They're mainly from the North Atlantic, but there's cores from the Pacific, Indian, and South Atlantic also. Now, this is just superimposing the isotope records from 0 to 750,000 and the paleointensity records on top of each other from 0 to 750. And this is from 750,000 to 1.5 million for the isotopes and for the paleointensity. And what we do is we use a tandem correlation of isotope and paleointensity records using the match routine, which was used by, devised by Lizecki and Lizecki in a paper in 2002, and used by Lizecki and Ramo to correlate their benthic isotope stack some few years ago now. We use this in tandem then to correlate both the isotope record and the paleointensity record together, so that we are optimizing the correlation of these two separate records. You start with the published age model. The records are divided into intervals, in our case 1 kiloyear intervals, and the routine minimizes the sum of squares of the differences to match intervals between records. Penalty functions are introduced to limit the likelihood of abrupt changes in sedimentation rate between and within records. And the beauty of this type of automated correlation is that it's repeatable. And also, if you're correlating isotope records and paleointensity records, even doing that manually is laborious, and doing it manually in a repeatable way is rather difficult. So this kind of automated correlation we find is actually very successful and very useful. How do we gauge whether, when we've used this match routine, whether we've actually improved the correlations? Well, one way to do it is to look at the squared wavelet coherence of two records. This is a record, the paleointensity record from 983 with the paleointensity record for 1308, and see whether the correlation, the coherence, is improved after matching. And the coherence here is gauged by the amount of red area you see here, which is at the 5% significance level. It's the coherence bordered by this heavy line. So having increased this area shown in red, we have some reason to believe that we have improved the match, before match and after match, for these two paleointensity records. We can also look at the same two records, but the isotope records. And again, the wavelet coherence map shows that the match routine has improved the correlation of the two isotope records. Now, we could do that for every pair of records we have, but we could summarize that data in a table like this, where this is the proportion of significant area on those wavelet coherence maps, and we can also run just a straight correlation coefficient to gauge whether the match routine has actually improved our correlation. And in all cases it does. So then we're left with a stack, not only of the isotope records, but also the paleointensity records. And the red curve is the new stack with a 2 sigma error in gray. And the blue here is the Lisecki-Ramo stack, LRO4. This is from 0 to 750,000 years. This is the paleointensity stack, shown in red with a gray error, 2 sigma error on it. And the blue here represents the SINT 2000 stack. This is the isotope stack from 750 to 1.5 million, and the paleointensity stack from 750,000 to 1.5 million. You can see that the new stack shows a lot of extra detail that's not seen in the SINT 2000 stack. Okay, but also the ISO stack, or the isotope stack, compares very well with the Lisecki-Ramo stack. So just looking at this paleointensity stack now and comparing it with the age of excursions that we talked about earlier, we can see that all the minima are associated with ages of excursions, or many of the minima. All these minima here are associated with ages of recorded excursions. If we attempt to calibrate the paleointensity stack, and the way we did this was by using a mean value from Tellier determinations for the Bruins, and then setting the minimum, which was the Cobb Mountain, the minimum value for paleointensity, to 7.5 microtesla, which was it's a method suggested actually by Constable and Tux about 10 years ago, which you strip off the dipole component from the modern field and look at the average field that you'd see when you stripped off that dipole field. And we set the minimum then to that value. And this is the calibrated VADM then from the paleointensity stack. And what's interesting is the excursions appear to, when that value of VADM dips below 2.5 times 10 to the 22 amp meter squared, as if there's some sort of threshold value when excursions are likely to occur. Let's now look at the wavelet power spectrum associated with this new stack. And that's shown here, where period is shown here. This is age, and these white dashed lines represent orbital periods, the orbital periods. Now, in the new stack, which is showed here, we don't see a lot of significant orbital power. In fact, we see less orbital power in the new stack than what's observed in the SINT 2000 stack. Now, in the new isotope stack, this is what the wavelet power spectrum looks like. It has characteristic 41 and 100 kiloyear power, and it's very, very similar to if you ran the same routine on the LRO4 stack. You see very much similar picture. So the isotope stack has a lot of the characteristic orbital power. The paleointensity stack does not. When we compare the new paleointensity stack with the isotope stack, in fact, we see very little coherence, which is good, because we wouldn't want our paleointensity stack to be, of course, coherent with our isotope stack. This brings us on to the issue of orbital power in paleointensity records. There's been a lot of literature about this in the last 10 or 15 years, and it's never been really put to rest. And we wanted to test this by looking at a different population of paleointensity and isotope records, some from the Pacific. These are records published by Hornung in 2002 and 2003. This is Site 1089 from Joe Stoner, and this is mainly our work from North Atlantic. And we wanted to first run these wavelet power spectra and see where the power is in the different paleointensity records. And we can see that this is 983, and we see orbital power, some orbital power in the 100 kiloyear period, some in the 41 kiloyear period. In a lot of these records, and particularly 919, we see a lot of 100 kiloyear power in that paleointensity record. This is the new 1308 record that we're using as a reference record for our stacks, and we see a little bit of orbital power, but rather limited in extent. Looks like it may be orbital power. So, but when we go to the Pacific, these two Pacific records are apparently devoid of any significant orbital power. And so this orbital power appears to be peculiar to the Atlantic records that we've studied. Now, the easiest way to leak orbital power into a paleointensity record is through the normalizer, which is ARM in most cases. And so we can look at this by studying the coherence between the paleointensity record and the normalizer. And there are some patches of coherence at 5% significance between the paleointensity records and ARM, but it's sort of patchy, and it's not very convincing. It's also clear that there's these arrows, which you can hardly see here, represent the phase relationship between the paleointensity and the ARM, and the phase relationship is inconsistent, which leads us to believe that perhaps the source of the orbital power that we see in these paleointensity records is not leaking into the paleointensity record through the normalizer, which is the lab magnetization we use to normalize the record. So where is it coming from? Well, we could test a number of different parameters, non-magnetic parameters or grain size parameters, but the most convincing one that we found, where it appears that we're seeing significant coherence between the paleointensity record and the parameter, is for a grain size parameter, ARM over IRM. And in fact, this ARM over IRM parameter appears to show more coherence with the paleointensity record than any other parameter. It also shows coherence with the isotope records, particularly for site 983. If we look at just simply that proxy, which is a grain size proxy for site 983, you can see how it's co-varying with the Delo-18 record from that site, which is shown in blue, and in green is this grain size proxy, where how to read these grain size proxies, the interglacials represent coarser grain sizes. So we clearly have at this site a grain size variation which is in sync with the Delo-18 record. Now, the explanation for that is probably related to the overflow water, the vigor of overflow water from the Norwegian Greenland Sea. These drifts are seeing then grain size changes that's associated with the vigor of overflow water, which is related to the formation of North Atlantic deep water. And these grain size changes are leaking into the paleointensity records, particularly from these sites. All, however, is not lost, because we think that this contamination, which we believe is related to this grain size variation, in fact, we can seek to try to understand how important it is for individual paleointensity records by filtering it out using various types of filters. And so for two sites, 983 and 984, we endeavored to do this. This is the actual paleointensity record, and this is the filtered record, just using different types of filters to filter out that orbital power. And in fact, the form of the curve doesn't change very much, and when we do the same operation on site 983, it doesn't change very much. So it's clear that this contamination is not debilitating to the paleointensity record. Indeed, the fact that we could generate a paleointensity stack which was consistent with the isotope data from the Atlantic to the South Atlantic to the Indian Ocean and to the Pacific tends to indicate that, in fact, these paleointensity records are not overly contaminated because in the stack, they're derived from very different climate regimes. We could test those correlations by looking at, again, these types of coherence maps, where we can look at how the paleointensity records compare from, say, the Atlantic to the Pacific, and gauge how much coherence there is just by using these types of maps. So in conclusion, I would conclude that excursions are brief polarity crons bounded by full polarity reversals. They are often incompletely recorded. The fact that they're full polarity reversals implicates the dipole field. Some Bruns Arctic excursions are associated with negative inclination NRM components carried by orthogenic gregite, possibly magnetized by partial self-reversal. If excursions are part of a continuum with polarity crons, we should expect to observe many more excursions in the last 2 million years, perhaps up to 35 per million years. If this is unreasonable, which I think it probably is, excursions must be distinct from polarity crons, possibly due to the role of the inner core. Coupled oxygen isotope and paleointensity records can enhance stratigraphic resolution by matching two independent global signals in tandem using this match routine. The resulting match results can be stacked to yield what we call piezo stacks. Although the iso stack has the expected orbital power spectrum, the RPI stack is almost devoid of orbital power. Orbital periods in some RPI records could be attributed to climate contamination. Magnetic grain size parameters, particularly ARM over IRM, show coherence with these contaminated RPI records. The contamination, however, is not debilitating to the RPI record that is largely controlled by the global field, at least for sedimentation rates less than 20 centimeters per 1,000 years. And that's it. Thank you.
I'd like to thank Jim very much for that presentation. We could take a few questions if there are some in the audience. If I can. In that case, I'll take my privilege and say I'm curious about your conclusion that the excursion process is distinct based on the idea of the Poisson process as a reversal recorder. Are you assuming that the Poisson process there is constant in time, the rate is constant in that analysis?
I mean, it's an imperfect simulation, but what I was trying to get at was try to predict whether the population of excursions that we're observing is consistent with a process that's a continuum with normal polarity reversals. I don't believe that's the case, partly because of that analysis, but partly because of the duration of excursions, which we find that the duration of excursions, the entire excursion, which must involve two reversals, is less than the reversals associated with major polarity crons. In other words, the Bruns-Matayama boundary, the reversal process takes maybe 5,000 years. That duration of polarity reversal is greater than the total duration of the best recorded excursions. So I think actually that what I was trying to prove there was that I think they're actually part of it. The mechanism is different. That's what I'm trying to say.
Jean-Pierre.
I didn't try that. You know, we're really, once we get, as you know, once we get back beyond a few 100,000 years, we don't have many records to play with, you know, that have both isotope and paleointensity records. So, you know, splitting them up into region, you'd run into the problem that you have very few records to play with, and that's why I lumped everything together. But I was encouraged by the fact that the stack, the 2 sigma error on the stack was quite small, even lumping everything together.
years or 5,000 years. And that is, well, in a way, contradictory to having a Poisson process, because the Poisson process assumes that the spectrum is continuous from zero. And so I think to strictly apply the Poisson process to the model reversal is perhaps not relevant. And if we take this, the period needed for reversal process, then perhaps the Poisson process can embrace expansion.
Yeah. Well, of course, you're exactly right. That's the modeling assumes instantaneous reversals, which is unrealistic. So, but I fully agree. I mean, I knew I'd get into trouble with the Poisson process.
As predicted. If there are no more questions, I'd like to thank Jim very much for my talk.